Alright, so this video will be on how to solve a two-dimensional motion problem where two objects are moving, one in the x direction, one in the y direction, and we need to find something about the result of that motion. So let's read our problem statement and see what we have. A canoer paddles across a river, starting at rest and accelerating at 0.8 meters per second squared east for 7 seconds. If the constant velocity of the stream or the river is 3.1 meters per second south, find the total or resultant displacement, delta R, of the canoer as seen by an observer on shore. So over here we have a bit of a diagram or picture of what's going on. We have north, east, south, and west. So our canoer is traveling east across the river is traveling south, or flowing south. Now an observer on shore would see the path of the canoer travel both across the river and downstream. So the dotted line here indicates the path seen by the observer that the canoer takes. This path represents two things. First, we can find a displacement, delta R, of the total displacement from final position to initial position for the canoer along this path. So that's delta R. We could also find a velocity, the average velocity, V average, that the observer sees the canoer have as they travel across the river. So we're not going to do V average for this problem, but you would find them in very similar ways. If we draw this dotted line as a triangle, we have our X direction and we have our Y direction. So in the X direction, the canoer is paddling across the river. In the Y direction, the river is flowing down. And this is our resultant delta R. So our displacement delta R will be found by combining the horizontal displacement delta X and the vertical displacement delta Y. If we can find delta X and delta Y, we can use them, and the fact that this is a right triangle with our X and Y always at right angles to each other, and we can find delta R using Pythagorean theorem. So our goal to get to delta R will be first find delta X and delta Y. In order to do that, we'll have to use our knowns and unknowns in the problem and some of our equations of motion to solve for the displacements delta X and delta Y. We will also need to report a direction on our delta R. In order to do that, we'll need to find an angle theta. So we'll get to that and we'll use some inverse trigonometry to find our angle theta. First, let's look at our knowns and unknowns for the problem and see if we can find delta X and delta Y. First, we know that our canoer is starting at rest. So as they travel horizontally across the river, Vx initial, their initial horizontal velocity is 0 because they start at rest. Next, we are told they accelerate in the x direction, so our a subscript x is equal to 0.8 meters per second squared. And this is east, which in our case is to the right. The time this takes is 7 seconds. So we know that our time in this problem will be 7 seconds as the canoer paddles across the river. Now, to get delta x from all this information in the x direction, we know our initial velocity, but we don't yet know the final. If we could find our final velocity, we could figure out how far the canoer traveled in this time with an initial velocity of 0. We could use, there's a couple ways we could actually go about this. We could use the first equation on our sheet. We could use Vx equals Vx initial plus Axt. This is a completely valid way to solve the problem. If we find the final velocity here, we could find the difference between, or the average between, not the difference, just the average between Vx final and Vx initial. If we find that average velocity for x, we could use that to find our displacement in the x direction. However, that's kind of a two-step solution for finding delta x, where the very next problem, or the very next equation on our equation sheet will get us directly to delta x. So the second equation says delta x equals Vx initial t plus 1/2 axt squared. Now we have all this information. We have Vx initial, we have ax, and we have t. So we can find our delta x using this equation. Let's go ahead and do that. So Vx initial is t, which means this whole term right here, 0 times t, that will just be 0. So our delta x is equal to 1/2 times our acceleration in the x direction, which is 0.8 meters per second squared to the right, times our time squared, which is 7 seconds squared. We're going to have seconds squared in the numerator and seconds squared in the denominator, so those units will cancel out, leaving us with meters, which is good because we want to report a displacement, which should be in meters. So if we do the math here, 7 squared should be 49, so we'll take 49 times 1/2 times 0.8. This gives us 19.6 meters. So our delta x is 19.6 meters to the right across the river. This is the horizontal distance that our canoer travels, their horizontal displacement from here to here. Again, we could report this as a distance if we didn't have our direction, but we're going to report it as a vector, a displacement with our direction to the right. So delta x is a 19.6, we can put that in here, 19.6 meters to the right. Great, now we just need to find delta y. We have a little bit more of given information. They said the constant velocity of the river is 3.1 meters per second south. So with a constant velocity, let's go ahead and erase this x equation to make room for our y. And we'll solve for delta y. So we still have our time. Time is equal to 7 seconds. And we said that our constant velocity in the y direction is 3.1 meters per second south. In our case, south is downwards, so we'll go ahead and put down. You could also write south for your direction, but I'm just noticing that in my problem, I can just as easily write down with the descriptive diagram that I've drawn. So this is our velocity. Now this we could describe as the average velocity in the y direction. We could also describe it as the initial or final, so Vy0 or Vy. All of those are correct because the initial, the final, the average, all the velocities are the same. This is a constant velocity, it will not change. The river is flowing at the same velocity the whole time. So with a constant velocity, if this does not change, we can use the equation V average equals, and we'll keep it in the y direction, Vy average equals delta y over delta t. Now this is saying if we can have a constant velocity or the average velocity for the whole time, we can find the total displacement traveled in the vertical direction due to the velocity of the river if we take the time and multiply it times our velocity for the river. So delta y is equal to 3.1 meters per second times 7 seconds. Let's go ahead and do the math there. 3.1 meters per second downwards times 7 seconds, which gives us a delta y equal to 21.7 meters. This displacement delta y is downwards on our diagram, or to the south. So now we have delta y in addition to delta x. Delta y equals 21.7 meters downwards. All right, great. So now we have both sides, except for the hypotenuse here, of our right triangle. We can now use Pythagorean theorem to say delta r squared is equal to delta x squared plus delta y squared. So if we add delta x squared to delta y squared, 19.6 squared and we should keep our units in here just to be correct. 19.6 meters squared plus 21.7 meters squared that will give us delta r squared. So we'll take 21.7 squared plus 19.6 squared. This gives us 855.05. Now our units for this, as we squared our meters, should be meters squared, which should tip us off that we're not quite done yet. To find our displacement delta r, we do have to take the square root of this. So we'll take the square root of 855.05, and then when we do that, we'll take the square root of meters squared for our units and get back to meters, which is what we want for our displacement delta r. Taking the square root of 855.05, I get delta r is equal to 29.24 meters. Great, so now we have the magnitude of our displacement here. However, we are not quite done yet because we need to report a direction with our displacement delta r. So whenever you're reporting a vector value like displacement, we need to report not only the magnitude with its number and its units, but also the direction that it's in. That's where we'll need to find theta. We can use any trig function. I'm going to use my favorite trig function, sine, and we'll use the inverse of this trig function to find theta. So if we set this up, the sine of my angle theta is equal to the opposite side, delta y, or 21.7 meters, divided by the hypotenuse of the triangle, delta r, which is 29.24 meters. So this is equal to, let's do this math, .74. All right, so 0.74 is equal to the sine of my angle theta. In order to find just theta, my angle, I'll need to take the inverse sine of this number. So I'll go ahead and take the inverse sine of 0.74, which gives me 47.9 degrees. So we can report our final answer. Just going to erase this here to make room. Delta r is 29.24 meters, and it's at an angle of 47.9 degrees, as shown on my diagram. The reason I put this little phrase in here is just to clarify. So if I didn't tell you that it was as shown on my diagram, we wouldn't really know. Is it below this x-axis, above it? Is it from the y-axis? So this establishes which angle we're talking about and where it is. So go ahead and just, as you make a diagram on your problem, draw the angle on there. When you report your answer, refer to it as shown on your diagram. Great, so we were able to use our equations of motion to use our given or known information, solve for delta y and delta x, which we then used with the Pythagorean theorem to say that delta r is equal to the hypotenuse of this triangle, and we used an inverse trigonometric function to find our angle theta. Great, so this is how we go through a two-dimensional motion problem to take motion in the x direction and the y direction, combine it to find the resultant motion, and find our displacement, resultant displacement delta r. Again, we could also do the same thing with velocities. If we had an average x velocity for that x period and an average y velocity for our y direction, we could combine them in the same way with Pythagorean theorem to find the average total velocity traveled along this diagonal line by our canoer. All right, thanks for watching.